KEQ calculations. So we use our KEQ value as a numerical way of being able to say something about the reaction. At the very least, we can figure out whether or not something is at equilibrium or not, and then we have a sense as to which way it might have to shift in order to achieve equilibrium if it's not at equilibrium. Finally, we can use our KEQ calculations to be able to figure out what the equilibrium concentrations will be once my reaction reaches equilibrium. So first and foremost, just doing the KEQ calculations, there are two things to always remember. First, it's important to write the KEQ expression. That's without any sort of numbers in it, just a reminder of what's supposed to go on top and what's supposed to go on bottom. Remember to only include gases or aqueous solutions. So if something's a solid or a liquid, it's not included in the KEQ expression. Once you have that, you plug in the numbers and solve. Remember that KEQ has no units, and remember that the brackets mean molarity, or moles per liter. So here's an example of a type of situation. The given reaction below, calculate the KEQ if 2 moles of N2 gas, 6 moles of H2 gas, and 5 moles of NH3 gas exist at equilibrium in a 3-liter container. So what this is saying is that this reaction is already at equilibrium. These are the moles of gas that exist in this container, and you're trying to get a sense as to what that KEQ value is. So again, you start with writing the KEQ expression. This is the reaction below. So I write my products over my reactants. All of these are gases, so I can include them. And I have to remember that these coefficients in front of each substance become the exponent. So because there's a 2 in front of the NH3, I put NH3 squared. There is nothing in front of N2, so that just becomes N2. And there's a 3 in front of the H2 as a coefficient, so that becomes the exponent. So my KEQ expression would be the concentration of NH3 gas squared over the concentration of N2 gas times H2 gas cubed. Because these are concentrations, I have to remember that it's in moles per liter. So my values were given as moles, and then I was told that it was in a 3-liter container. So I first have to calculate the concentrations of these gases. So I place it over the 3-liter container. So I divide all of my moles of gas by my 3-liter container. So 5 moles divided by 3 becomes 1.6 molar. 6 divided by 3 equals 2 molar. And 2 divided by 3 equals 0.6. It's actually 0.7, but rounding, you get the idea. So I plug these values into my KEQ expression. So it's 1.6 squared over 0.6 times 2 cubed. And that becomes 0.5325. Here's another reaction. Given the following reaction, if the KEQ value is 2.6 and the concentrations of H2 and I2 gas at equilibrium equal each other and equal 1.8 molar, what is the concentration of HI gas? So here I'm given the KEQ value and 2 of the 3 gas concentrations, and it's a matter of being able to find out what the concentration at equilibrium is of that third gas. So again, I start by writing the KEQ expression. So because my HI gas is my product, that goes on the top, so HI squared, because again the coefficient is 2, over H2 times I2 gas. And that equals 2.6. It equals 2.6 because I was given that KEQ value. So I then plug in my values. I don't know my HI concentration, but both my H2 and my I2 gases are 1.8 molar. So I don't have to divide by the volume of the container because I'm giving you the concentrations in molarity, so I don't have to do anything extra. So then I'm just solving for my unknown, and my unknown ends up being 2.9 molar. So what I did was I multiplied 2.6 by 1.8 squared, and that gave me 2.9 molar. Now example C, the KEQ value, you're trying to find the KEQ value of this reaction is 4 times 10 to the negative third. Again, there's no units, it's just a dimensionless constant. Dimensionless just means there's no units. So what's the KEQ value of the reverse reaction? So you'll notice that at the top here, this is a composition reaction, and its KEQ value is 2.6. Sorry, it's a composition reaction. This is under different conditions. And it's saying that the KEQ value of this composition reaction right here is 4 times 10 to the negative third. The question then is, what's the KEQ value of the decomposition reaction? So what's really important to understand is that these two reactions are opposites of one another. So my KEQ expression will then be reversed, right? This would be a product, these would be reactants, so this would be HI squared over H2 times I2. It's going to be the reciprocal of that for this reaction, right? What used to be the reactants are now the products. What was the product is now the reactant. So because the second equation is the reverse of the top, right, composition, decomposition, then the KEQ value of this reverse reaction, the decomposition reaction, is going to be the reciprocal of the KEQ value of my forward reaction. So in this case, my KEQ value of my forward reaction under these circumstances was 4 times 10 to the negative third. So my KEQ value for the reverse reaction will be 1 over 4 times 10 to the negative third, or 250. So a couple of take-homes. One, between example B and example C, you'll see that the KEQ value for the same reaction is different. That's because KEQ values are very temperature and pressure specific. So just because I say the KEQ value for this is 2.6, that doesn't mean that under different circumstances, it's a very, very different KEQ value. This will be important in the future when we start talking about ways to be able to take advantage of that and shift things in our favor if we want to increase the amount of products that we have. Secondly, it's always important to write the KEQ expression first. That means the KEQ value of my products over my reactants, with the coefficients becoming the exponents. Thirdly, it's really important to remember that my concentration units have to be in molarity. So if I'm given moles and liters, I have to first calculate molarity. And then finally, because if you have any sort of opposite reaction, like in this case a composition reaction, and then the other case a decomposition reaction of the same thing under the same circumstances, then the KEQ of my reverse reaction will be the reciprocal, or 1 over, the KEQ value of my forward reaction.